Hello, and welcome to Learn When You Sleep, where the universe opens its strangest doors just as your eyes begin to close. Tonight, we are going to wander into one of the most unsettling corners of theoretical physics. Not the cold silence of a distant void, not the slow spin of a dying star, but something far closer to impossible. Something that should not exist by the rules your mind has learned to trust. We are going to talk about a black hole made entirely of light. Take a moment, wherever you are right now. Maybe you are lying in a quiet room with the window cracked just slightly, and the world outside is already dark and still. Maybe there is a lamp somewhere nearby, casting a soft, warm glow across the ceiling. Maybe the only light is the faint blue shimmer of the screen you are holding. Look at that light for just a moment, whether it is a candle or a bulb or the cold gleam of a phone in the dark. Really look at it. Notice the way it fills the space around it without effort, without weight, without any sense of pressing down on the surface it falls on. Notice how it arrives instantly, how it asks nothing of the air it passes through, how it seems to belong to the category of things that simply are, without cost or consequence. Because tonight, that light is going to become something terrifying. We take light for granted in a way we take almost nothing else for granted. It fills our mornings before we are even fully awake. It guides our evenings as the sun pulls away from the horizon. It carries information across entire galaxies and arrives in our eyes after traveling impossible distances in a single breath of time. We flip a switch and we expect it. We open a curtain and it floods in. Light is so constant and so ubiquitous that it has become invisible to us in the most ironic sense. We see everything by it, and we rarely see it at all. We think of it as weightless. We think of it as free. We think of it as the opposite of heavy things, the opposite of dense things, the opposite of things that press and pull and hold and trap. A feather falling in sunlight seems less substantial than the light it falls through. A beam of light from a torch does not bend the beam back toward the torch. A laser pointer does not sag toward the ground. Light moves in straight lines and asks nothing of the surfaces it illuminates and leaves no mark on the space it passes through. And yet the universe has something to say about that picture. And what it has to say is delivered not in words but in equations, in the calm and utterly indifferent language of mathematics, which does not care what we find comfortable or intuitive or safe. The equations say that light is not what we think it is, not in the extremes, not when you press it far enough, not when you concentrate it and focus it and push it past every threshold that ordinary experience has taught you to believe in. What if I told you that light can become a black hole, not a metaphor, not a poem, not a way of saying something clever about vision or knowledge or the things we cannot see. A real, physical, gravitational trap made entirely of the most weightless, the most untouchable substance in the universe. A black hole that does not come from a collapsing star or a dying sun, but from light itself, focused and compressed, and so incredibly dense that it folds space around itself and traps everything, including the very photons that created it. This is called a Kugelblitz. The name comes from the German, and it means ball lightning. It is a name that captures something of the visual paradox at the heart of the concept. A ball of lightning, a sphere of blazing, brilliant, impossible fire. But what a Kugelblitz actually describes is something far stranger and far more powerful than any lightning storm you have ever imagined or ever will imagine. It is a theoretical object, a prediction born from the deepest equations of general relativity, one of the most well-tested theories in the history of human thought. It is not science fiction. It is science that fiction has barely caught up to, and in some ways never will. So tonight, we are going to move slowly through this idea. We are not going to rush it. We are going to treat it the way it deserves to be treated, with patience and care and the kind of attention that lets each new layer settle before the next one is added. Because a Kugelblitz is not just one strange thing. It is a chain of strange things, each one following logically from the last, each one strange in its own right, until you arrive somewhere that feels completely unacceptable to common sense, but is fully supported by the mathematics of the universe. And the mathematics of the universe do not apologize. They simply are. Wherever you are right now, let your body find its most comfortable position. If you are lying down, let your spine release a little into whatever surface is beneath you. If you are sitting, let your shoulders drop. Let your jaw unclench. Let your hands rest open rather than closed. The universe is about to ask you to hold some very large ideas, and it is easier to do that when the body is not gripping anything. Along the way, we are going to ask some questions that do not have easy answers. Can light be heavy? Can something weightless become the heaviest thing imaginable? Can the very substance that fills the universe with warmth and vision and color, the thing that has been the companion of every living creature that has ever opened its eyes, become a trap so absolute that nothing, not even its own relatives, not even other photons, can ever escape? The answer, quietly terrifying as it is, appears to be yes. But before we get to the monster, we have to understand the paradox it is born from. And that paradox begins with the most famous equation in the history of human thought. You have seen it on t-shirts and coffee mugs and the walls of science classrooms. You have heard it spoken aloud in documentaries and films. You may know it so well that you have stopped really hearing it. But tonight, we are going to hear it again, very slowly, as though for the first time. As though you are reading it on a chalkboard in a quiet room somewhere. The chalk still fresh, the equation written by a hand that understood what it meant and was slightly astonished by it. E equals mc squared. 5 symbols, 3 concepts. And hidden inside those 3 concepts, one of the most radical ideas the universe has ever offered to the human mind. The idea that energy and mass are not 2 different things. They are the same thing, wearing different clothes, speaking different languages, appearing in different circumstances, but fundamentally, at the deepest level of what they are, identical. Think about what that means for a moment. Really let it sit. You are made of mass. Your body, your bones, your blood, the solid physical presence of you in this room at this moment is mass. And energy is what makes things move and change and burn and glow and carry signals across nerve fibers and power the thoughts you are having right now as you lie here. For most of human history, mass and energy were completely separate categories. Things either had weight or they had the ability to do work. They were not the same. Einstein said they are. Mass is just a very concentrated, very stubborn, very organized form of energy. And energy, in the right circumstances, in the extreme circumstances, can behave like mass. It can warp space. It can generate gravity. It can, in principle, become a source of gravitational pull so powerful that it traps everything around it. Now, light is made of photons, and photons are famously, technically, massless. They have no rest mass. If you could somehow stop a photon, which you cannot, because light can never be at rest, it would weigh nothing at all. This is why light travels at the speed of light. Only massless things can travel at the speed of light. A photon's zero rest mass is not a quirk or a coincidence. It is a fundamental property of what a photon is, written into the structure of the universe itself. And yet, a photon carries energy. An enormous amount of energy, depending on its frequency. The photons of visible light carry enough energy to trigger the chemical reactions in your eye that you experience as sight. The photons of ultraviolet light carry enough energy to damage the DNA in your skin cells. Gamma ray photons, which are just photons at the extreme high energy end of the electromagnetic spectrum, carry so much energy per photon that they can knock electrons loose from atoms, penetrate solid matter several centimeters deep, and cause radiation damage deep inside living tissue. They are, in their own right and in their own way, one of the most violent things in the universe. And they are light, massless, weightless, traveling always at the speed of light. Light. So here is the question that breaks everything open. If energy and mass are the same thing, and if photons carry energy, even though they have no rest mass, does that energy still generate gravity? Take a breath before you answer, because the answer changes things. The answer is yes. This is where the mind starts to slip just slightly, just enough to feel it, because we are used to gravity being about mass. Planets have mass. Stars have mass. Black holes have enormous mass. Gravity is about the pull between massive things. That is what we learned. That is what Newton told us, more or less. And Newton was not wrong, exactly. He was just incomplete. He was giving us the view from the living room of a house whose basement and attic were still unexplored. Einstein explored the rest of the house. Einstein's general relativity describes gravity not as a force between masses, but as a curvature of space-time caused by the presence of energy and momentum. Not just mass, energy. All forms of energy contribute to the curvature of space-time. And curved space-time is what we experience as gravity. A photon has no rest mass, but it carries energy and momentum. Therefore, a photon warps the space-time it passes through. The effect of a single photon is so vanishingly small that you will never notice it. A beam of sunlight does not pull you toward it. A flash of lightning does not bend the room around it. The gravitational effect of ordinary amounts of light is so tiny that it takes instruments of extraordinary precision to detect it at all. And even then, the effect is not the gravity of the light itself, but the light's role in revealing the gravity of other things. But what happens when you take an extraordinary amount of light and you focus it into an extraordinarily small space? What happens when the energy density, the amount of energy packed into a given volume, climbs so high that the gravitational effect of all that concentrated light is no longer negligible? What happens when it grows and grows and grows, until the curvature of space-time around that tiny bright point becomes so extreme that even the photons themselves cannot escape the curvature they have created? What you get, if the mathematics are to be believed, and the mathematics have been remarkably trustworthy so far, is a Kugelblitz, a black hole made of light. Let that image sit with you for a moment. Not the image of a dead star crushed under its own weight, cold and dark and massive. Not a dark remnant of something that once burned and now no longer does, but a blindingly bright, impossibly energetic concentration of pure radiation that curves space-time so severely around itself that it becomes its own prison. Light trapping light. Energy become gravity. The most visible thing in the universe turning itself into the most invisible. There is a moment in the logic of a Kugelblitz, a precise threshold, a mathematical edge that exists at a calculable point in space and a calculable density of energy, where the light goes from unimaginably bright to completely invisible. Not because it fades, not because it dims or cools or slows, but because the curvature of space around it crosses a critical point, and the light that was radiating outward in all directions finds that the curved geometry of space no longer allows outward to exist. Every direction curves back inward. Every path, no matter how it begins, ends inside. The light that created the black hole becomes the first prisoner of the black hole it created. And from the outside, you see nothing. Not because nothing is there, but because the most intense concentration of light that has ever existed in this corner of the universe has just wrapped itself in darkness so complete that it has become, in the most literal sense, a black hole. The darkness is not absence. The darkness is the signature of the most extreme presence. This is the paradox at the heart of a Kugelblitz, blinding light that creates absolute darkness. A thing born in the most extreme brilliance, that ends in the most extreme invisibility. The contrast between what creates it and what it becomes is so sharp, so total, so complete, that it almost feels like a cosmic joke, a riddle with a punchline that upends everything you thought you understood about the relationship between light and dark, between brightness and shadow, between presence and absence. But the universe is not joking. The universe is following its own rules with perfect mathematical precision, without sentiment, without irony, without any awareness of how strange the outcome seems to the minds that live inside it. And those rules, followed to their logical conclusion, lead here, to a ball of light that is also a black hole. In the parts that follow, we are going to unpack each step of this process. We are going to understand, slowly and gently, what it means for energy to have gravity. We are going to walk through the concept of a Schwarzschild radius, the mathematical threshold that separates light from darkness, presence from oblivion. We are going to meet John Wheeler, the physicist who first seriously explored this idea. We are going to contemplate what a Kugelblitz would actually look like in the moments before it crossed that threshold. And we are going to follow the idea forward into time, into the far future, where some theorists believe that a Kugelblitz might be the most powerful and most dangerous engine ever conceived by any civilization anywhere in the universe. But that is ahead of us. Right now, in this quiet moment, just let the central idea settle like a stone dropping through still water, sending its rings outward slowly, one after another, each one reaching a little further than the last. Light can become a black hole, not as a metaphor, not as a dream, as a physical, mathematical, gravitational fact. The warmth on your skin from a sunny afternoon, the glow of a fire on a cold evening, the soft light of the room you are in right now. These are all, in some sense, infinitely diluted relatives of a force that, at the right concentration, could fold space itself into an inescapable prison. The same physics that governs the gentle photons touching your closed eyelids right now also governs, at its extreme end, the creation of something from which not even those photons could ever return. The universe has rules, and those rules have no exceptions. They apply to everything, including light, especially light. And those rules say that if you pour enough light into a small enough space, the light stops being light in any sense you would recognize. It becomes something ancient and terrible and dark. Let your breath slow. Let the room around you soften at the edges. We are going to walk into the heart of this idea very carefully, and there is no need to rush. The Kugelblitz has been waiting, theoretically, since the first equations of general relativity were written down over a century ago, in the mind of a man who was already astonished by what his own mathematics was telling him. It can wait a little longer while we find our footing. The question is simple, even if the answer is not. Can light be heavy? And the deeper we go, the more clearly the answer reveals itself. Not heavy in the way a stone is heavy, not massive in the way a planet is massive, but subject to gravity, capable of generating gravity, and at the extreme edge of what physics allows, capable of becoming gravity itself, turned inward, sealed, permanent, dark. That is where we are going tonight, into the place where light becomes its own undoing, into the place where the most familiar force in nature reveals its most alien face, into the Kugelblitz. There is a version of the universe that makes intuitive sense. In this version, heavy things fall and light things float. Rocks sink in water and feathers drift on air. Planets pull moons into orbit and moons pull oceans into tides. Gravity, in this familiar version of things, is about weight. It is about mass. It is about the stubborn solidity of matter pressing on space and demanding to be noticed. It is the force you feel in your legs when you stand up, in your chest when you lift something heavy, in your body when it tells you that down exists and that you had better respect it. This is the universe as we feel it, and it is not wrong. It is just a corner of the larger picture. And then there is the actual universe, The actual universe is stranger and more generous and more terrifying than the intuitive one. In the actual universe, gravity is not just about mass. It is about energy. All of it. Every form of energy that exists contributes to the curvature of space-time, and that curvature is what we call gravity. The intuitive version was not wrong, exactly. Mass is a form of energy, a very dense and concentrated form, and so the heavy things do fall and the planets do pull their moons. But it was incomplete. It was a map that showed the roads but left out the mountains. And the mountains include light. To understand why light has gravitational influence, even though it has no rest mass, we need to understand something about what mass actually is. Not what it feels like to hold something heavy in your hand, but what mass is at the level of the equations that govern the universe. Because mass, it turns out, is not the simple and irreducible thing we once thought it was. It is not a basic property like charge or spin that a particle simply has or does not have without explanation. Mass is something that emerges from something deeper. Mass is, in a very precise and well-tested sense, a measure of resistance to acceleration. Push something and it moves. The easier it moves, the less mass it has. The harder it resists, the more mass it has. You feel this every time you push a shopping cart. An empty cart rolls away easily. A full one requires real effort. The difference is mass. But what determines that resistance at the fundamental level? What is it, deep inside an object, that makes it reluctant to change its motion? The answer, according to the deepest understanding we have, is energy. Specifically, the energy of the interactions that hold matter together. The protons and neutrons inside an atom contain quarks, and those quarks are bound together by the strong nuclear force, which is one of the four fundamental forces of the universe and arguably the most powerful. The binding energy of that force, the energy locked up and holding the quarks together, contributes directly to the mass of the proton or neutron. Here is the part that should stop you for a moment. Most of the mass of ordinary matter, most of the mass of you and of this room and of everything you have ever held in your hands, does not come from the quarks themselves. The quarks are actually very light. It comes from the energy of the interactions that hold them together. Mass is, in a very real and measurable sense, frozen energy. It is energy that has become so tightly organized and so deeply bound that it behaves like a solid, tangible thing with weight and inertia and heft. Einstein's equation captures this with a precision that is almost uncomfortable. E equals mc squared. The c squared term is the speed of light multiplied by itself, which is approximately 900 quadrillion meters squared per second squared. That is an enormous number. It is so large that it tells you something about the universe that is difficult to absorb. A single gram of matter, if it could be entirely and perfectly converted to energy, would release enough to level a large city. Not because of anything special about that gram of matter, but because the conversion factor between mass and energy, the c squared, is so extraordinarily large. And the conversion goes both ways. If you can get enough energy into a small enough space, you can create mass where none existed before. This is not speculative. Particle accelerators do exactly this every day in laboratories around the world. In the Large Hadron Collider at CERN, protons are accelerated to within a fraction of a percent of the speed of light and then smashed together. The kinetic energy of those collisions, the energy of motion, is so extreme that it produces new particles, new mass, born entirely from the energy of the collision. Particles that did not exist a moment before appear in the wreckage of the impact, created from pure kinetic energy according to E equals mc squared. Mass and energy are convertible. They are the same currency in different denominations. You can exchange one for the other at the rate set by c squared, and gravity responds to both. Now, a photon has no rest mass. This is true and important and worth sitting with for a moment. If you could somehow bring a photon to rest, hold it still in space, which you cannot, because stopping a photon is not something the universe allows, it would have zero mass. Precisely zero. Not approximately zero, not very nearly zero, but exactly zero. This is not a measurement limitation. It is a fundamental property of the photon, written into the structure of the standard model of particle physics. But a photon is never at rest. That is the other side of the same coin. A photon is always moving at the speed of light. Always. In every reference frame. In every circumstance. A photon has never been at rest and can never be at rest. And this is not a technical limitation, but a consequence of what a photon fundamentally is. And that constant motion at the speed of light carries momentum. Real, physical, measurable momentum. And momentum, like energy, contributes to the stress-energy tensor. The stress-energy tensor is the mathematical object in Einstein's general relativity that sits on the right side of the field equations and determines how spacetime curves. It includes contributions from mass, from energy, from pressure, and from momentum. All of these things curve spacetime. All of them generate gravity. A photon, as it moves through spacetime, carrying its freight of energy and momentum, creates a tiny, fleeting distortion in the fabric it passes through. Imagine spacetime as a vast, flexible surface, not a flat rubber sheet, which is the simplified version you may have seen in textbook diagrams, but something far more complex and far more beautiful, a four-dimensional fabric whose geometry is determined at every point by the total energy and momentum present there. In the simplified version, you place a heavy ball on the sheet and it sags, creating a depression, and other objects rolling across the sheet are deflected toward it. That cartoon captures something real about gravity, the way mass warps the space around it. But the full picture includes more. It includes energy of all forms. It includes pressure. It includes momentum. A photon moving through this fabric makes a mark. The mark is so small, for a single photon, that no instrument has ever detected it directly. The gravitational field of a single photon is unmeasurably tiny. But the principle is there, encoded in the equations, real in the mathematics, waiting for the scale to become large enough that it matters. To feel this in your imagination, try the following. Picture a single candle flame in a dark room. The flame emits photons in all directions, warm orange photons in the visible spectrum, infrared photons you feel as heat on your skin, a few ultraviolet photons invisible to your eyes. Each of those photons carries a tiny amount of energy and momentum. The gravitational influence of all those photons together is so minuscule that it would not move a single atom of dust. The candle is not a gravitational object. It is a light source. Now imagine 10 candles. Now 100. Now 1,000, clustered together in a space the size of a marble. The light is now intensely bright, and the heat is dangerous at close range. But the gravitational effect is still far too small to matter in any practical sense. You would not be pulled toward the cluster of candles by anything other than their warmth. Now imagine not 1,000 candles, but the total light output of the sun, all of it, every photon the sun emits in an entire second, which is an amount of energy so large that if it were delivered to Earth, it would vaporize the planet instantly, focused into a volume the size of a marble. Now the situation has changed. The energy density is now so extreme that the radiation pressure alone would be enough to push ordinary matter away with tremendous force. The temperature at the focal point would be in the tens of billions of degrees. And the gravitational effect of all that concentrated energy, while still small compared to any planetary mass, is beginning to become real. Now imagine 1,000 suns worth of light compressed to a point the size of an atom. Now imagine 1,000,000. Now imagine the total light output of the entire Milky Way galaxy, every star in it, all 400 billion of them, every photon from every nuclear furnace in the galaxy, concentrated into a volume smaller than a proton. At some point along this path of imagination, a point that can be calculated precisely using the equations of general relativity, the energy density of the concentrated light crosses a threshold. The combined gravitational effect of all those photons, all that energy, all that momentum, becomes so extreme that the curvature of space-time around that tiny point crosses a critical boundary. The curvature becomes so severe, so completely folded inward, that the photons themselves, traveling at the speed of light in every outward direction, find that every path they can take leads back inward. There is no outward anymore. The geometry of space has changed so completely that outward is no longer a direction that exists. The light has trapped itself. This is not a mechanical trap, like a mirror bouncing photons back. It is not that the photons are hitting a wall and bouncing. It is that the shape of space itself has changed so fundamentally that the paths light can travel do not include any that lead away from the center. You could think of it this way. Imagine you are always walking forward, always moving ahead as fast as you possibly can, never slowing, never stopping. But the landscape you are walking through is curved, gently at first, barely noticeable, and then more and more steeply, until the forward direction you are always walking is no longer pointing anywhere, but down and in, so that no matter which way you start out, your path always curves back toward the center. You are not being stopped. You are not being slowed. You are moving at maximum speed in every moment. But forward, for you, no longer means away. It means back toward the center. Every path, at maximum speed, leads inward. That is, very roughly, what happens to light at and inside the event horizon of a Kugelblitz. The light does not slow down. It cannot slow down. It travels always at the speed of light. But the space it travels through is curved so severely that speed in any direction is speed toward the center. The weight of light, not the literal weight of a photon at rest, which is zero, but the gravitational consequence of energy so concentrated that it bends the universe around itself. This is mass in the only sense that ultimately matters to gravity, not rest mass, not the stubborn solidity of atoms, but the deep currency of energy and momentum that all of physics trades in. And you might ask, as it is reasonable to ask, whether we have ever seen this principle at work in any form we can actually observe, rather than just in the equations. The answer is yes, in several ways that are less dramatic but equally instructive. In the very early universe, in the first fractions of a second after the Big Bang, the universe was filled with a plasma so hot and so dense that the energy density of radiation alone, not matter, but pure radiation, pure light in its most energetic form, dominated the total energy budget of the cosmos. The expansion of the universe in those first moments, the rate at which space itself grew, was governed not by the gravity of matter, but by the gravity of light. The universe was, in a meaningful and calculable sense, ruled by the gravity of photons in those first instants. And we can see the fingerprints of that era in the cosmic microwave background, in the ratios of light elements, in the large-scale structure of everything we can observe. The gravity of light shaped the universe we live in. It was not a small effect, and it was not theoretical. It was the dominant gravitational force in the cosmos for tens of thousands of years. Gravitational lensing offers another example, one we can observe directly with telescopes. When light from a very distant galaxy passes near a massive object, a cluster of galaxies for instance, the gravity of that cluster bends the path of the light, creating arcs and rings and multiple images of the distant source. We observe this regularly. It is one of the most powerful tools of modern cosmology. And the same equations that describe light being bent by gravity also describe light generating gravity. The effect is immeasurably small for ordinary amounts of light, but the physics is there, the same physics, the same equations, the same principle. The weight of light is not a poetic idea. It is a physical reality, tested and confirmed across a century of observation, embedded in the most successful theory of gravity ever constructed. What makes a Kugelblitz different is not a new principle. It is the application of a completely familiar principle to an unfamiliar, extreme, almost incomprehensible scale. As you rest here, let that idea find its place in your understanding. The light around you, however soft and however ordinary, is subject to gravity and generates gravity. Its contribution is negligible, unmeasurable, effectively zero. But the physics is not zero. The physics is real, and at the extreme edge of what the universe allows, that physics leads to the Kugelblitz. The weight of light, small now, in this room, absolute at the threshold, and beyond the threshold, the event horizon, the darkness, the silence. The weight of light is real, and when it becomes real enough, it becomes everything. Every great idea in physics has a moment of origin. Sometimes it arrives in a sudden flash, a thought experiment on a train, or a daydream in a patent office. A moment when the mind is loose enough to catch something that more rigid thinking would have missed. Sometimes it emerges slowly from years of calculation, a conclusion that the equations have been pointing toward long before anyone was brave enough to follow them to the end. A destination visible only to those willing to keep walking when the path becomes uncomfortable. The Kugelblitz belongs to the second kind. It was not a sudden inspiration. It was not a eureka moment. It was a destination that the mathematics of general relativity had been waiting to reveal since the theory was first written down. A prediction embedded in equations that were complete before anyone had fully explored all of their consequences. The Kugelblitz was always there in the math. What took decades was the willingness to look at the math and follow it honestly into the territory it was pointing toward. The man most associated with that honest following was an American physicist named John Archibald Wheeler. If you have spent any time reading about black holes or quantum gravity or the large questions of theoretical physics, you have encountered Wheeler's influence even if you have not encountered his name. He was one of the most remarkable minds of the 20th century, and also one of its great coiners of phrases. He had a gift that is rarer in physics than raw mathematical ability, the gift of finding the right words for the most wordless things, of naming ideas in ways that made them suddenly graspable. In the history of science, there are those who discover and those who translate, and Wheeler did both with extraordinary facility. He gave us the term black hole, before Wheeler popularized that name. In a famous lecture in 1967, physicists were still referring to completely collapsed objects as frozen stars or gravitationally collapsed objects. The phrases were accurate but clumsy, and they failed to capture the defining feature of these objects, which is not that they were once stars or that they were frozen, but that they were holes, regions of space-time from which nothing escaped. The term black hole captured that essence in 2 words, and it spread through physics and then through popular culture with a speed that itself seemed to approach the speed of light. He gave us the term wormhole, the geometric shortcut through space-time that connects 2 distant regions of the universe. He gave us the term quantum foam, the description of space-time at the Planck scale as a seething, fluctuating, probabilistic structure that bears no resemblance to the smooth and continuous space of everyday experience. He gave us the phrase it from bit, his suggestion that physical reality at its most fundamental level might be informational, that existence itself might be built from questions and answers rather than from particles and fields. Wheeler had a way of taking the most abstract and mathematically dense ideas in physics and giving them a form that the mind could hold. And it was Wheeler who took seriously the question of what general relativity predicted would happen if you concentrated not matter, but pure electromagnetic radiation into a small enough region of space. The theoretical work on this question had roots that went back to the very beginning of general relativity itself. Einstein's field equations, published in 1915, describe how energy and momentum curve spacetime. The right side of the equations contains the stress-energy tensor, which includes contributions from all forms of energy. This means, if you read the equations carefully, that a sufficiently intense concentration of electromagnetic radiation, photons packed tightly enough, would appear in the equations as a source of spacetime curvature, just like a concentration of matter would. The math makes no distinction. It simply responds to energy density, in whatever form that energy takes. In the decades following Einstein's work, physicists occasionally considered these so-called electromagnetic geons, the name Wheeler gave to bound configurations of electromagnetic fields held together by their own gravity. The idea was simple to state and extraordinarily difficult to analyze. Could you build a stable or quasi-stable object out of nothing but electromagnetic radiation, held together by the very gravitational field its energy generates? Wheeler was perhaps the most serious and systematic explorer of this territory. In the 1950s and 1960s, he investigated whether such objects could exist within the framework of general relativity, and he brought to that investigation both his mathematical ability and his characteristic willingness to follow the equations wherever they led. The answer, as he found, was complicated and in some ways disappointing, and in other ways deeply illuminating. Pure electromagnetic geons turned out to be unstable. They tended to disperse rather than hold together. The electromagnetic repulsion between the photons, combined with the dynamics of the radiation field, made it very difficult to maintain a bound state over any significant period. Geons would form, in a theoretical sense, and then fall apart, their constituent photons scattering outward rather than remaining in a stable orbit around their common center of mass. But the instability of the geon did not mean the Kugelblitz was impossible. It meant something more precise and more interesting. It meant that if you wanted to create a black hole from light, you could not do it by simply gathering photons into a gentle cluster and waiting for them to find their equilibrium. You would have to do something more violent and more sudden. You would have to compress the radiation so quickly and so completely that it crossed the critical threshold before the instability had time to scatter the photons apart. Picture it this way. Imagine trying to build a tower out of water. If you stack water gently, it simply flows away. The structure has no time to form before the material disperses. But if you compress water fast enough, harder than it can respond to in the available time, you can create a state in which the water behaves like a solid for a brief moment. The Kugelblitz is something like this. You cannot build it gently, but you can perhaps create it suddenly, in a single catastrophic act of concentration that crosses the event horizon threshold before the radiation has time to disperse. This distinction matters enormously for how we think about making a Kugelblitz. It is not a slow and careful assembly. It is not something that can happen gradually or be approached incrementally. It is an event, sudden and catastrophic and irreversible, in which the energy density of light crosses a specific mathematical boundary so quickly that the curvature of space-time around the concentration becomes an event horizon before anything can escape. And that specific mathematical boundary has a name that you may have encountered before, perhaps in a documentary about black holes, perhaps in a science article you read once and half remembered. It is called the Schwarzschild radius. Karl Schwarzschild was a German physicist who did something remarkable under circumstances that were themselves remarkable. In 1916, he was serving in the German army on the Russian front during the First World War. He was not in a comfortable office or a well-equipped laboratory. He was in the field, surrounded by the chaos and destruction of one of the most devastating conflicts in human history. and he received a copy of Einstein's newly published general relativity field equations, and he sat down, in whatever moments of quiet the front could offer, and found the first exact solution. The Schwarzschild solution describes the geometry of spacetime around a spherically symmetric, non-rotating, uncharged mass. It is an exact solution, not an approximation, and embedded within it, like a jewel hidden in the mathematics, was a critical radius. For any given mass, there exists a specific distance from the center at which something qualitatively different happens to the geometry of spacetime. If all the mass of an object could be compressed inside this radius, the curvature of spacetime at that radius would become so extreme that the escape velocity, the speed you would need to be traveling to leave from that point and never return, would equal the speed of light. Nothing in the universe can travel faster than light. This is not a speed limit in the way that traffic laws are speed limits, something that could be broken if you were willing to pay the fine. It is a geometric property of spacetime itself. Nothing can travel faster than light because the structure of space and time does not permit it. And if you need to travel at the speed of light to escape, and nothing can travel that fast or faster, then nothing can escape. That critical distance is the Schwarzschild radius. For the Earth, the Schwarzschild radius is about 9 millimeters. For the Sun, it is about 3 kilometers. For a stellar mass black hole of 10 solar masses, it is about 30 kilometers. These are the radii to which you would need to compress each of these objects to turn them into black holes. The Earth, compressed to the size of a marble. The Sun, compressed to a sphere smaller than a modest hill. The distances are small, but not zero. They are real thresholds. And now here is the crucial extension for our story, the step that takes the Schwarzschild radius from a curiosity about matter to the seed of the Kugelblitz. The Schwarzschild solution and the concept of the Schwarzschild radius was originally derived for mass, for matter, for the dense and solid stuff that stars and planets are made of. But the equations of general relativity, as we have already established, are not limited to matter. They respond to all forms of energy. And so, with the appropriate mathematical extension, the concept of a Schwarzschild radius applies to any concentration of energy, including pure electromagnetic radiation. What this means is that there exists, in principle, a threshold for any given concentration of light, a specific energy density in a specific volume of space, at which the combined gravitational effect of all those photons crosses the Schwarzschild boundary, at which the curvature of space-time inside that volume becomes so extreme that even the photons themselves cannot escape the curvature they have generated. The light crosses its own Schwarzschild radius, and in that moment, a Kugelblitz is born. Schwarzschild himself died on the Russian front, just months after completing his famous solution. He sent his paper to Einstein, who was astonished by the elegance of the result, and then he contracted a disease and died. He never lived to see the full implications of his work, never saw the black hole physics that grew from his solution, never saw the term Schwarzschild radius become one of the most important quantities in all of astrophysics. He never knew that his equation, worked out in the trenches of the First World War, would one day lead to the theoretical prediction of a black hole made of light. The birth of a monster, traced back to a quiet calculation in the middle of a war. This is how physics often works. The seeds are planted in one era, and the flowers bloom in another. Schwarzschild planted the seed. Wheeler tended it. And the Kugelblitz grew from soil that was prepared a century ago, in circumstances that could not have been further from a peaceful laboratory, by a mind that was doing what scientific minds do even in the worst circumstances. Following the logic, trusting the equations, seeing where they led. Close your eyes for a moment if they are not already closed, and let the image build slowly. Imagine that you are very far away, not in space the way you are used to thinking about it, not across a room or across a city or across a continent, but across several light years of interstellar space. You are safe. The distance is safe. And you have instruments, extraordinarily sensitive instruments, capable of detecting radiation across the entire electromagnetic spectrum, from the lowest energy radio waves to the most extreme gamma rays. And you are pointed at a specific location in space, a location where someone or something is attempting to create a Kugelblitz. The readings on your instruments begin to rise, slowly at first, so slowly that you might mistake it for background noise, for the ordinary hiss of the cosmos that your instruments always pick up at some low level. But the readings do not flatten. They climb, and as they climb, they do so across the full electromagnetic spectrum simultaneously, which is the signature of something extraordinary, because ordinary astrophysical processes tend to emit strongly in some parts of the spectrum and weakly in others. This signal is strong everywhere. The intensity climbs through orders of magnitude, first matching the output of a single ordinary star, then 10 stars, then 1,000, then a small cluster. These are numbers that would ordinarily be remarkable in their own right, events worth noting, worth publishing. But the reading keeps climbing. 100,000 stars, 1,000,000, 1,000,000,000, the output of a small galaxy, concentrated in a region that your instruments tell you is smaller than a planet. Your instruments begin to struggle. Their sensors were not designed for readings this extreme. The numbers at the high end of your spectrum, the gamma ray detectors, the X-ray counters, begin to saturate. You switch to a different mode, attenuating the signal, reducing your sensitivity so that you can continue to track what is happening. And what is happening is still climbing. The focal point, the tiny region in space where all the converging radiation is being directed, has now achieved an energy density that has no counterpart in the contemporary universe. It is briefly, and in a very small volume, recreating conditions that last existed when the universe was a fraction of a second old. The temperature at the focal point, if temperature is even the right word for something this extreme, is in the hundreds of billions of degrees. The radiation pressure is so intense that ordinary matter caught in the region would be disintegrated instantly, not burned, not vaporized, but stripped to fundamental particles and absorbed into the radiation field before any thermodynamic process could even begin. And then, in the time it takes light to cross the diameter of an atomic nucleus, the reading stops climbing. It does not fall. It does not explode outward. It does not produce a shockwave or a flash or any of the dramatic signatures of a conventional explosion. It simply stops. The intensity, which was climbing through values that your instruments could barely express, goes to zero. Not falls to zero, goes to zero. Instantly, the signal disappears as completely as if it had never existed. Your instruments show you the space where the Kugelblitz formed. It is unchanged in appearance. There is no visible object there, no glow, no shimmer, no residual radiation field. There is, if your instruments are sensitive enough, a very slight gravitational signature, the signature of a black hole of a certain mass at a certain location. But visually, optically, in every part of the electromagnetic spectrum, there is nothing. The light sealed itself away in the moment it created its own prison. Now let your imagination move closer, not to a safe distance, but to a dangerous one, a distance where the thought experiment becomes visceral. Imagine observing, somehow immune to all consequences, from just a few kilometers away from the focal point of a Kugelblitz formation. Not the astronomical safe distance of light years, but the intimate, terrifying distance of kilometers. At this distance, in the final seconds before the event horizon forms, you would be looking at something that has no natural analog. The convergence of radiation toward the focal point would not appear as a point to you at this distance. It would appear as a sphere of light, growing and intensifying as more and more of the directed radiation converges. The sphere would be visually overwhelming. not in the way that a bright light in a dark room is overwhelming, not in the way that looking at the sun is overwhelming, but in a way that makes both of those experiences seem dim and trivial. The peak emission of the Kugelblitz in formation is in gamma rays, far above the visible spectrum, invisible to human eyes. But the total energy density is so extreme that even the tiny fraction of the emission in the visible range would be brighter than anything the human visual system is designed to process. The retinal damage would be instantaneous and total. But suppose, in this thought experiment, that you could see without damage, that your eyes were somehow immune to the radiation. What would you see? You would see a sphere, not a smooth, quiet sphere like the surface of a planet or the face of the moon, but a seething, churning sphere that seems to boil at its surface. The secondary radiation, the particle-antiparticle pairs being created and annihilated in the radiation field, the X-rays and gamma rays scattering off each other and off the plasma they create, would give the surface of the sphere a texture, a turbulence, an appearance of something that is simultaneously burning and crackling and blazing in every direction at once. Around the sphere, a corona of secondary effects would extend outward like a halo. Electrons and positrons, created in the intense radiation field, would spiral outward and then be pulled back, creating a shimmering, unstable boundary region between the heart of the convergence and the empty space beyond. The corona would be visible as a haze of light around the central sphere, softer and more diffuse than the blinding core, but still incomparably bright. And then the event horizon forms. The sphere vanishes, not dramatically, not with a final burst. The sphere is there, and then it is not. In the time it takes light to cross from one side of the event horizon to the other, the transition from the brightest thing imaginable to absolute darkness is complete. The corona persists for a brief moment, the secondary radiation still propagating outward from the region, and then it too fades as its source disappears behind the horizon. And what remains is empty space with a very small and very dark gravitational singularity at its center. This is the luminous horror of a Kugelblitz, and the horror is worth naming carefully because it is a specific kind of horror. It is not the horror of darkness in itself. We are accustomed to the idea that black holes are dark. The horror is in the contrast, in the speed and totality of the transition. The most extreme brightness becomes the most extreme darkness, not gradually, not through any process of cooling or dimming, but instantaneously, in the moment the geometry crosses its threshold. The light does not go anywhere. This is the crucial point. The light does not escape and disperse. The light does not burn out. The light is still there, inside the event horizon, still blazing with the full energy that was concentrated into the formation. Inside the Kugelblitz, in the fractions of a second after the event horizon forms, the radiation field is unchanged in its intensity. The photons are still present, still moving at the speed of light, still filling every cubic centimeter of the interior with their furious energy. The brightness has not diminished by a single photon, but the geometry has changed. And because the geometry has changed, no signal of that brightness can reach the outside. The light is trapped. The blazing is sealed. The intensity persists inside, invisible to any observer outside the event horizon, permanent for as long as the Kugelblitz maintains its mass. Two states, simultaneous, separated by a mathematical surface. Inside, the most intense radiation environment that can exist. Outside, nothing. This is the deepest visual paradox of the Kugelblitz. It is not that the light went away. It is that the light is unreachable. The same photons that were, moments ago, blazing outward in all directions are now sealed in geometry that permits no outward direction. They are as present as ever, as energetic as ever, as numerous as ever. They simply cannot tell the outside universe that they are there. There is a philosophical dimension to this that pulls at the mind like a current pulling at a swimmer. We use light, always, as our signal for presence. If something is there, we expect to be able to see it, or at least detect it with some instrument sensitive to some part of the electromagnetic spectrum. The universe has always, until black holes, played by this rule. Things that are there can in principle be detected. Things that cannot be detected in any way are not, in any operationally meaningful sense, there. A Kugelblitz breaks this rule with the most extreme possible example. The brightest thing that can exist is also the most undetectable thing that can exist. Not because it does not emit radiation. It emits radiation more intensely than anything in the known universe. But all of that radiation is trapped behind the event horizon. The brightness is perfect and total and utterly inaccessible. We use light as a metaphor for knowledge, for revelation, for understanding. We say that science illuminates. We speak of being in the dark when we are confused and of finding the light when we understand. These are not arbitrary metaphors. They reflect something deep in our experience. The way that vision has always been our primary means of knowing the world. The way that light has always been the carrier of information about what is there. A Kugelblitz takes the maximum possible amount of light and makes it into the minimum possible source of information. The most intense radiation that can exist, producing no detectable signal whatsoever. The most extreme light, creating total informational darkness. And from the outside, you see nothing. You see a black sphere, if your instruments are good enough to detect the gravitational lensing of background light around the event horizon. You see, perhaps, a slight distortion in the images of stars behind it, the bending of their light as it passes near the black hole's gravity. You see, in the most technical sense, a mass at a location, expressing itself through gravity alone. And inside, blazing with the fire of the early universe, sealed forever in the geometry it created, the light that made the Kugelblitz continues its furious and invisible dance. The luminous horror, the blinding that creates blindness, the light that seals itself so completely that even its existence cannot be communicated to the universe it left behind. Let that image rest with you as your breathing slows. The sphere that was blazing, the moment of transition, the silence that follows, the light, still raging somewhere, sealed beyond reach. Two extremes, existing simultaneously, separated by a threshold so precise and so absolute that it might as well be the boundary between two different universes. The Kugelblitz has a face, but you can only see it in the moment before it becomes itself. After that, there is nothing left to see. Only the dark shape of what was once the most extreme light in this corner of the cosmos. The blinding darkness. The dark that comes from too much light. The seal that comes from too much brightness. The silence that follows the most violent thing the universe can produce. This is the face of the Kugelblitz. To understand where a Kugelblitz comes from, in the deepest sense, you have to go back. Not back a few centuries to the birth of modern physics, not back a few billion years to the formation of the first stars, or the first galaxies, or the first atoms. You have to go back to the very beginning of everything, to the first fraction of a second after the Big Bang, when the universe was not the vast, cool, structured place we observe today, not the place of spiral galaxies and quiet solar systems and small blue planets, where creatures lie in the dark and wonder about physics, but a seething, unimaginably hot plasma in which the distinction between matter and radiation was barely meaningful, and in which the energy density of light alone was enough to curve space-time on cosmic scales. We spoke earlier about the weight of light, about how photons, despite having no rest mass, carry energy and momentum, and how that energy and momentum contribute to the curvature of space-time, producing real gravitational effects. In the universe today, this effect is negligible for any ordinary amount of light. The energy density of the radiation field in our current universe is so low, so diluted by 13.8 billion years of cosmic expansion, so thinned and cooled and spread across the vast dark reaches of the cosmos, that its gravitational contribution is a rounding error compared to the gravity of matter. Light is present everywhere in the universe today, in the form of the cosmic microwave background and the light from stars and galaxies, but it is dilute as a breath in a cathedral, present but not dominant. But the universe was not always like this. There was a time, early in the universe's history, when the situation was completely reversed, when radiation was not the quiet background but the dominant actor, when light was not the passenger but the driver, when the gravity of photons was not a rounding error, but the primary force shaping the structure and evolution of the cosmos. To reach that time, we need to go back. And as we go back, through billions of years of cosmic history, we watch the universe change. The galaxies we know, the great structures of the cosmic web, the filaments and voids and superclusters, these dissolve as we reverse time. The stars wink out, one by one, their nuclear fuel unburning, their matter dispersing back into the gas clouds from which they formed. The gas clouds themselves merge and smooth as we continue backward, the density of the universe rising and the temperature climbing, the structures of the cosmos dissolving back into the uniformity of an earlier time. Keep going, past the formation of the first stars, past the epoch of reionization when the first light flooded the young universe, past the time of recombination when electrons and protons first joined into neutral hydrogen atoms and the universe became transparent to light, releasing the radiation we now detect as the cosmic microwave background, past all of that and further, into the first few 100,000 years of cosmic history, when the universe was still a plasma too hot for atoms to survive, when electrons and protons existed separately, and when the temperature was tens of thousands of degrees everywhere. Even here, the universe is already inconceivably different from anything we experience today. But we need to go further still, into the first seconds, into the first milliseconds, into the first microseconds. In the very beginning, in the first second after the Big Bang, the temperature of the universe was in the billions of degrees. In the first millisecond, it was in the trillions. In the first microsecond, the temperature was so high that the energy of a typical photon was comparable to the mass energy of a proton. This means that photons were energetic enough to spontaneously create proton-antiproton pairs from the vacuum, and those pairs, in turn, annihilated back into photons in a constant, furious exchange. Matter and radiation were interconverting continuously, so rapidly and so completely that the distinction between them had almost no meaning. The universe was a single, unified thing, a plasma of such extreme energy that every particle and every photon was constantly transforming into every other. And in this state, the energy density of radiation, of light in its most extreme and energetic form, dominated the total energy budget of the universe. Not by a small margin, by an overwhelming one. Matter, in the sense of particles with rest mass, was present but was a tiny fraction of the total energy. The universe was, in the most physically meaningful sense, made of light. Radiation was the universe, and the gravity of that radiation was what determined how the cosmos evolved. This period of cosmic history is called the radiation-dominated era, and it lasted from the very beginning until the universe was roughly 50,000 years old. For those 50,000 years, the expansion rate of the universe, the temperature, the density, the geometry, everything was determined primarily by radiation. The gravity of photons and other massless particles shaped the fabric of the young cosmos. And the energy densities involved, in the earliest moments of this era, were extraordinary beyond any ordinary astronomical description. They were not just high. They were the highest that the laws of physics we understand allow for an extended region of space. They were, in every meaningful sense, the conditions inside a Kugelblitz, applied to the entire universe rather than to a microscopic volume. When physicists describe the conditions in the very early universe and the conditions inside a forming Kugelblitz, they use the same mathematics, the same equations, the same physical framework, because they are describing the same thing at different scales and in different circumstances, but governed by the same fundamental physics. The early universe was a Kugelblitz, not a localized one, not a microscopic one, but a cosmic one. A Kugelblitz the size of the universe itself, expanding rather than collapsing, but characterized by the same extreme radiation density, the same dominance of light over matter, the same physics in which the gravity of photons is not negligible but central. This connection is more than a metaphor. It is a physical statement about what makes the early universe and the Kugelblitz the same kind of phenomenon at their respective scales. And it has consequences for how we think about what a Kugelblitz is and where it comes from and what studying it might teach us. Were those early conditions sufficient to create Kugelblitz naturally, localized ones, in the conventional sense? This is a fascinating question, and the answer involves one of the most intriguing theoretical objects in modern cosmology. In a universe so hot and so dense that the energy density of radiation was extreme everywhere, local fluctuations in that density could, in principle, have created regions where the energy density briefly exceeded the Schwarzschild threshold for a microscopic volume. Not everywhere, not in every region, but in the rare and extreme tails of the statistical distribution, in the places where density fluctuations happen to pile up unusually. In these places, the concentration of radiation would briefly and locally recreate the conditions that define a Kugelblitz. The energy density would cross the event horizon threshold. A black hole would form, not from matter, not from a collapsing star, but from the concentration of radiation itself. A primordial Kugelblitz, born from the radiation-dominated plasma of the early universe. These hypothetical objects belong to a broader class called primordial black holes, a concept developed and explored by Stephen Hawking, Bernard Carr, and others in the 1970s. The idea is that the extreme conditions of the early universe could produce black holes through density fluctuations, regardless of whether the fluctuating material was matter or radiation. A primordial black hole formed during the radiation-dominated era from a fluctuation in the radiation field rather than from a concentration of matter would be precisely the kind of Kugelblitz we have been discussing. The mass of such a primordial Kugelblitz would depend on when during the early universe it formed. Black holes formed at earlier times, when the universe was hotter and denser, would be smaller because the horizon size, the maximum region that was causally connected at any given moment, was smaller at earlier times. A primordial black hole formed in the first second of cosmic history would have a mass comparable to the Sun. One formed in the first microsecond would be far smaller, perhaps a fraction of a gram. And one formed in the earliest moments of cosmic history, when quantum gravity becomes important, would be a Planck mass black hole, the smallest black hole that our current physics can meaningfully describe. Whether any of these primordial Kugelblitz actually formed depends on the details of the early universe that we are still working to understand. The amplitude of the density fluctuations in the early radiation field is the key quantity, and it is constrained by observations of the cosmic microwave background, by the abundances of light elements forged in the first 3 minutes, by the large-scale structure of the galaxy distribution. Current observations suggest that the density fluctuations were not large enough to produce primordial black holes in enormous numbers. But they do not rule out the possibility that some formed, particularly during specific phases of early cosmic history, such as phase transitions, or during the end of cosmic inflation, when conditions were especially likely to produce large density fluctuations. The search for evidence of primordial black holes is an active and energetic area of research. Gravitational microlensing surveys look for the characteristic brightening of background stars when a compact object passes in front of them. Gravitational wave observatories listen for the mergers of black holes that might have masses characteristic of primordial formation. Gamma-ray observations scan the sky for the characteristic bursts that would accompany the final evaporation of primordial black holes that formed in the early universe and are only now reaching the end of their Hawking evaporation lifetimes. No confirmed detection has been made, but the searches continue because the stakes are high. Finding primordial black holes would be finding evidence of the most extreme physics of the early universe, preserved and present in the cosmos today. But the connection between the Kugelblitz and the early universe goes deeper than the question of whether primordial black holes formed. It goes to the heart of what a Kugelblitz means as a concept. When we think about creating a Kugelblitz artificially, through the deliberate focusing of radiation, we are, in a very precise physical sense, trying to recreate in miniature the conditions that prevailed everywhere in the universe in its first fractions of a second. We are trying to take a tiny volume of space and fill it with the energy density that once characterized the entire cosmos. We are trying to build a small piece of the early universe, here, now, in the cool and structured and matter-dominated universe of the present. Think about that for a moment. The universe around you is old and cool and structured. It has had nearly 14 billion years to expand and dilute and organize itself into galaxies and stars and planets and the quiet room you are lying in. The radiation that once dominated everything has thinned to a whisper, the cosmic microwave background at 3 degrees above absolute zero, barely detectable, a ghost of the fire that once ruled everything. The universe has moved so far from its original state that the conditions of its birth seem almost unimaginably foreign. A Kugelblitz would recreate those conditions. In a volume far smaller than an atom, for a time far shorter than a heartbeat, the energy density of the beginning would return. The fire of the first moments would burn again, sealed in its own event horizon, a bubble of the early universe suspended in the calm and aging cosmos. And in that fire, in that recreation of the beginning, there is something that transcends physics. There is a connection to the very origin of everything. The atoms in your body were forged in stars. The stars formed from gas clouds. The gas clouds condensed from the matter produced in the Big Bang. The Big Bang itself began in conditions that were, in their essential physics, the conditions of a Kugelblitz. Follow the chain of cosmic history back far enough, back through 14 billion years of expansion and cooling and structure formation, back through the formation of galaxies and the ignition of the first stars and the recombination of the first atoms, back through the seething plasma of the radiation-dominated era, and you find conditions that look like the inside of a black hole made of light. The universe did not begin in darkness. It did not begin in cold. It did not begin in the quiet and the structure we associate with home. It began in conditions so extreme, so energetic, so filled with light in its most violent form, that the concept of darkness did not yet exist. The Kugelblitz is a piece of that original state, a relic of the conditions from which everything we see today ultimately descended. When you look at the night sky, you see the great-grandchildren of the radiation era. Every star you see is a nuclear fire, a pale and structured echo of the conditions that once prevailed everywhere. Every photon that enters your eye has traveled from some distant source, carrying a tiny fraction of the energy that once, in those first moments, dominated the entire universe. And the Kugelblitz, if one were ever created, would be something different. Not an echo, a recreation, a piece of the beginning momentarily present in the middle of cosmic history. Let that thought move through you slowly. The quiet room you are in, the soft sounds of a world at rest. And somewhere in the mathematics, in the equations that describe this peaceful moment and also describe the first instant of time, the connection between where you are and where everything began. The Kugelblitz is new and ancient at once. It is a concept born from the mathematics of the 20th century that describes conditions as old as the universe itself. Anyone willing to follow those equations to their most extreme conclusions will find it there, written in the same language that describes the birth of the cosmos. The early universe was a Kugelblitz, and a Kugelblitz is a piece of the early universe. The circle closes. The beginning and the extreme end of our physics meet in the same equations, the same energy densities, the same geometry of light and gravity, and the threshold between them. Let your breathing carry you deeper into rest, and let the image of the early universe settle beside the image of the Kugelblitz. Two things that are, at their core, the same thing. One vast and cosmic and lost to time. The other tiny and theoretical and perhaps, someday, possible. Both made of the same fire. Both described by the same equations. Both pointing back to the moment when the universe was nothing but light, and light was everything. A black hole that evaporates. When you first hear this phrase, it sounds like a contradiction so complete that it almost seems designed to confuse. Black holes are defined by their permanence, by the absolute and irreversible nature of the event horizon, by the fact that nothing escapes, by the darkness that has no end and the trap that has no release. The classical physics of general relativity is entirely clear on this point. An event horizon, once formed, admits no exit. The darkness is forever. The geometry of Norton does not have a return clause. And yet, in 1974, Stephen Hawking published one of the most unexpected and most profound results in the history of theoretical physics. A result so surprising that, when he first presented it to colleagues, many assumed he had made an error. A result that, once accepted, changed the picture of black holes in a way that has never been undone and that continues to generate research and controversy and deep questions half a century later. Hawking showed that black holes are not permanent, that they emit radiation, that they slowly, almost infinitely slowly in most cases, leak energy to the surrounding universe, that this leaking causes them to gradually shrink, and that a black hole, given sufficient time, will lose all of its mass and cease to exist, ending its life in a burst of energy whose nature and content remain one of the deepest unsolved problems in all of physics. This is Hawking radiation, and for a Kugelblitz, its implications are not just fascinating, they are transformative. They turn the Kugelblitz from a permanent and unreachable sealed prison into something far stranger and, in some ways, far more interesting. Something with a temperature, something with a lifetime, something that glows. To understand why a black hole emits radiation, and to feel why this is so strange, we need to think carefully about the nature of empty space. In classical physics, the vacuum of empty space is truly empty. It contains nothing. It is the complete absence of matter and energy, the background against which physical processes play out, itself contributing nothing. Empty space, in the classical picture, is a stage with no actors, a canvas with no paint. But quantum mechanics tells a radically different story about the vacuum. In quantum mechanics, the uncertainty principle, one of the bedrock principles of the theory, states that you cannot simultaneously know both the energy of a system and the time over which you are measuring it with perfect precision. The more precisely you pin down the time, the more uncertain the energy becomes, and vice versa. This is not a statement about the limitations of our instruments. It is a statement about the nature of reality itself. Energy and time are fundamentally complementary, and pinning one down necessarily blurs the other. This uncertainty has a remarkable consequence for empty space. Because the energy at any point in space is subject to quantum uncertainty, it fluctuates. On very short timescales, the energy at a point in the vacuum is uncertain, and this uncertainty allows for the spontaneous appearance of particle-antiparticle pairs. A photon and an antiphoton, an electron and a positron, a quark and an antiquark. These pairs can appear from nothing, exist for a time so brief that no classical measurement could detect them, and then annihilate back into nothing. The total energy of the process averages to zero over any observable time interval. So energy conservation is satisfied in the only sense that quantum mechanics requires, the statistical sense, the sense that averages work out even if individual moments fluctuate. These are virtual particles, and they are more than a theoretical convenience. Their effects are measurable. The Casimir effect, the tiny attractive force between two very closely spaced metal plates in vacuum, arises from the modification of virtual particle fluctuations in the space between the plates. It has been measured with extraordinary precision. Virtual particles are real in the sense that their effects are real, even though they are not directly observable. In ordinary empty space, far from any massive objects, virtual particle pairs appear and disappear symmetrically and leave no lasting trace. The two members of the pair remain close together, interact with each other, and annihilate. The vacuum fluctuates but remains, on average, empty. Near the event horizon of a black hole, the story changes. The event horizon is not an ordinary region of space. It is a boundary between two qualitatively different geometries, a surface beyond which the future is fundamentally different from the future on this side. When a virtual particle pair appears very near the event horizon, there is a small but non-zero probability that the pair appears at precisely the right location and with precisely the right configuration that one member of the pair finds itself inside the event horizon and the other finds itself outside. When this happens, the two members of the pair cannot annihilate each other. They are separated by the most absolute boundary in the universe. The one inside is now inside a black hole. The one outside is outside, and the event horizon between them is impassable. The particle that fell inside becomes, in a meaningful quantum mechanical sense, a real particle inside the black hole. The particle that remained outside also becomes a real particle, free to propagate away from the black hole into the surrounding universe. From the perspective of an observer far from the black hole, a real particle has appeared near the horizon and is traveling outward. The black hole appears to be emitting radiation, but energy must be conserved. If a real particle with positive energy has been created outside the black hole and is carrying that energy away, something must compensate. The mathematics of Hawking's derivation shows that the partner particle inside the event horizon carries, in the relevant quantum mechanical sense, negative energy, and that this negative energy is deposited into the black hole. The net effect is that the black hole loses a tiny, almost immeasurably tiny, amount of energy with each such event. Its mass decreases, imperceptibly slowly, but continuously. This is Hawking radiation. It is real radiation, thermal radiation, with a temperature that depends inversely on the mass of the black hole. The heavier the black hole, the colder its Hawking radiation. The lighter the black hole, the hotter. For the black holes we observe in the universe, the stellar mass black holes created by the deaths of massive stars, the Hawking temperature is extraordinarily small. A black hole with the mass of the Sun would have a Hawking temperature of about 60 nanokelvins, 60 billionths of a degree above absolute zero. The cosmic microwave background radiation, the faint thermal afterglow of the Big Bang that permeates all of space, has a temperature of about 2.7 Kelvin. The microwave background is tens of millions of times hotter than the Hawking radiation of a solar mass black hole. Such a black hole does not evaporate. It absorbs more energy from the microwave background than it emits via Hawking radiation. It is, in net terms, gaining mass, however slowly. These large black holes will not evaporate on any timescale that has meaning in the context of human history or even the current age of the universe. Their evaporation timescales are 10 to the power of 60, 70, or more years, numbers so large that writing them out in full would fill more pages than there are atoms in the observable universe. But here is where the Kugelblitz becomes extraordinary in a new and different way. The inverse relationship between mass and Hawking temperature means that a small black hole is hot. A very small black hole is very hot. And a microscopic black hole, the kind that a Kugelblitz of modest mass would be, is extremely hot. Not warm, not somewhat elevated in temperature. Extraordinarily, blazingly, catastrophically hot. A black hole with the mass of a small mountain, say 10 billion kilograms, would have a Hawking temperature of hundreds of billions of degrees. It would radiate intensely across the full electromagnetic spectrum, with peak emission in gamma rays. Its luminosity, in the technical sense of the total power it radiates, would be comparable to that of a nuclear weapon detonating every few seconds. A tiny, invisible, intensely hot point in space, glowing with gamma radiation and particle emission, slowly consuming itself. This is what a small Kugelblitz looks like from the outside. Not the featureless darkness of a stellar mass black hole, but a glowing, radiating, temperature point source, bright in gamma rays, shrinking as it radiates, its temperature climbing as its mass decreases, its luminosity increasing as it loses mass, in a runaway accelerating cascade that ends in a burst of energy releasing all of its remaining mass. The evaporation of a small Kugelblitz is not a gentle process. It does not wind down slowly and quietly like a clock running out of spring tension. It accelerates. As the mass decreases, the Hawking temperature rises, which means more radiation is emitted per unit time, which causes the mass to decrease faster, which causes the temperature to rise further, which causes more radiation, and so on, in a positive feedback loop that drives the evaporation faster and faster until the final moments, when the remaining mass is tiny and the temperature is enormous. Produce a burst of radiation whose energy is released in an interval of time so short that the burst appears essentially instantaneous. The final explosion of an evaporating Kugelblitz would release, in that brief interval, energy equivalent to the complete conversion of all the remaining mass to radiation via E equals mc squared. For a Kugelblitz of modest mass, this would be an explosion of extraordinary violence, localized to an extraordinarily small volume of space. The energy released per unit mass would exceed that of any chemical or nuclear explosion by many orders of magnitude. It would be the most efficient conversion of mass to energy that physics permits. This evaporation timescale has a precise formula. The evaporation time depends on the cube of the initial mass. Double the mass and the evaporation time increases by a factor of 8. Have the mass and the evaporation time decreases by a factor of 8. A Kugelblitz with the mass of a large mountain, roughly 10 billion kilograms, would have an evaporation time approximately equal to the current age of the universe, about 14 billion years. A Kugelblitz formed in the early universe with this mass would be just now, at this moment in cosmic history, reaching the end of its life, entering the accelerating phase of evaporation, approaching its final burst. Let that sit with you for a moment. If such primordial Kugelblitz exist, some of them may be, right now, in this moment, entering their final evaporation cascade somewhere in the universe. Tiny, invisible points of extreme gamma radiation, glowing more and more brightly, shrinking toward their final burst, preparing to release all of their remaining mass energy in a flash that would briefly outshine nearby stars. We have not detected any such bursts with certainty, but we have not ruled them out. We are still looking for a much smaller Kugelblitz, one with the mass of a few nanograms. The evaporation time would be measured in fractions of a second. Such an object would exist, in the full sense of being a black hole with an event horizon, for a time so brief that no human perception could register it. It would form and evaporate almost instantaneously, the event horizon appearing and disappearing before any macroscopic process could respond. It would leave behind only a brief, intense burst of high-energy radiation, a flash of gamma rays and other particles in the location where it formed. Now, here is where Hawking radiation becomes not just a physical curiosity, but a crucial feature of the Kugelblitz as a practical concept. Because the Hawking radiation of a small Kugelblitz is not just an interesting phenomenon. It is the mechanism by which a Kugelblitz releases its energy back to the universe, and controlling that release, directing it, exploiting its enormous power density, is the basis of the most extraordinary propulsion concept in theoretical physics. But before we reach that, let us sit for a moment with the thermodynamics of the Kugelblitz, because there is something philosophically remarkable embedded in Hawking's result that deserves its own space. Hawking radiation connects black holes to thermodynamics in a way that was completely unexpected and remains incompletely understood. Jacob Bekenstein, in the early 1970s, proposed that black holes carry entropy, encoded in the area of their event horizon, with the entropy proportional to the area in Planck units. This was a radical proposal because entropy is usually a property of systems with many internal degrees of freedom, many microscopic states. A gas has entropy because there are many ways to arrange the individual molecules to produce the same macroscopic properties. But a black hole, described by the no-hair theorem, has only three macroscopic properties: its mass, charge, and angular momentum. How could something so simple have enormous entropy? Hawking's result confirmed Bekenstein's proposal. A black hole with a given mass has a specific Hawking temperature, and a body with a temperature radiates with a specific entropy. The numbers worked out. The Bekenstein-Hawking entropy formula, which gives the entropy of a black hole as proportional to the area of its event horizon, is one of the most celebrated results in theoretical physics. It suggests something deep about the relationship between gravity, thermodynamics, and the nature of information. For a Kugelblitz, this has a particular resonance. The Kugelblitz is created from light, from photons, which are themselves the primary carriers of entropy in the universe. Stars radiate light, and that light carries entropy away from the star, increasing the total entropy of the cosmos. Light is thermodynamically one of the universe's most efficient entropy producers. When we create a Kugelblitz by focusing light, we are concentrating entropy into an event horizon. The entropy of all those photons becomes the Bekenstein-Hawking entropy of the black hole, and Hawking radiation slowly returns that entropy to the universe, leaking it back out in thermal radiation until the Kugelblitz has completely evaporated. The Kugelblitz borrows entropy from the universe in the most dramatic possible way, concentrating it in the most extreme possible configuration, and then returns it, transformed, over whatever timescale its mass and temperature determine. The second law of thermodynamics is satisfied. The universe's books are balanced. But the process of borrowing and returning is one of the most extreme thermodynamic cycles that the laws of physics permit. Let your breathing slow. Let the room you are in carry its ordinary sounds, the hum of something distant, the settling of a structure in the night, the quiet rhythm of a world at rest. And let the image of the Kugelblitz evaporating settle into your thoughts. The black hole made of light, slowly releasing its energy back to the universe in a thermal glow. The most extreme darkness, gradually brightening as it shrinks, its temperature rising, its luminosity climbing, approaching the final burst that will release everything it holds. The darkness has a lifetime. The event horizon has an expiration. And in the end, transformed and randomized and released into the universe as thermal radiation, the light comes back. Not the same light. Not the coherent, directed, focused gamma rays that went in. But energy, the same total energy, returned to the cosmos in the most disordered and spread out form that physics allows. Hawking radiation is the universe's way of saying that even the most extreme act of concentration, even the sealing of light inside its own event horizon, is not final, not permanent, not forever. The universe will have its energy back, eventually, in its own time, in its own way. The darkness ends. The light returns, different and late and transformed beyond recognition. But back, there is a dream that has lived in the hearts of physicists and engineers and science fiction writers and ordinary people who have looked up at the night sky long enough to feel the pull of it. The dream of traveling between the stars, not visiting our nearest neighbors in the solar system, which is already an ambition of extraordinary technical difficulty, but crossing the real distances, the distances between suns, the light years of empty interstellar space that separate our star from every other star we have ever seen. The night sky, to anyone who has really looked at it, is not just beautiful. It is an invitation that cannot be accepted, and the impossibility of accepting it is one of the quiet griefs of being human at this particular moment in history. The stars are there. They have been there every night of every life ever lived on this planet. They have guided sailors and inspired poets and anchored the navigation of every civilization that has looked upward. And yet not a single human being, not one, has ever traveled to any of them, or stands any realistic chance of doing so in any near future lifetime. The distances are too great. The physics are too demanding. The nearest star system to Earth is Alpha Centauri, a triple system of two sun-like stars and a small red dwarf, about 4.37 light-years away. This sounds like a modest distance when you say it in those words. 4 1/3 light-years. But a light-year is the distance that light, traveling at 300,000 kilometers per second, covers in an entire year. 1 light-year is roughly 9.5 trillion kilometers. 4 light-years is roughly 40 trillion. The fastest spacecraft we have ever built, the Voyager probes launched in 1977, are now traveling at about 60,000 kilometers per hour. At that speed, reaching Alpha Centauri would take approximately 70,000 years. Not 70 years, 70,000. Even at the relatively modest goal of 10% of the speed of light, a speed we have no current means of achieving for any crewed or even sizable uncrewed spacecraft, the journey to Alpha Centauri would take about 44 years. A human lifetime of travel in each direction to reach the closest point of light in the night sky. And Alpha Centauri is the closest. The galaxy is 100,000 light-years across. The distances to other interesting destinations, other potentially habitable systems, the great nebulae and clusters, and the galactic center, are measured in thousands and tens of thousands of light-years. True interstellar travel, travel that would make the galaxy accessible, requires speeds that make 10% of light speed look leisurely. This is the wall that stands between us and the stars. Not a wall of physics in the sense of something forbidden. The physics do not forbid fast travel. They demand a price for it. And the price is energy. Enormous, staggering, civilization-scale quantities of energy delivered efficiently and continuously over years of travel. This is the rocket equation problem, and it is one of the most intractable constraints in all of spaceflight thinking. To accelerate a spacecraft, you must expel propellant in the opposite direction. Faster propellant, expelled more of it, gives you more acceleration. But the propellant has mass. Carrying more propellant means your spacecraft starts heavier, which means you need more propellant to accelerate it, which means you carry more mass, which means you need more propellant still. The cycle escalates exponentially. For chemical rockets, reaching even a fraction of a percent of the speed of light would require a spacecraft that is almost entirely fuel, with the actual payload, the thing you actually wanted to send, being a negligible fraction of the total mass. What you need to escape this trap is an energy source with an extraordinarily high energy density. Not just high, extraordinarily high. The highest energy density available from conventional chemistry is the burning of hydrogen and oxygen, which releases roughly 15 megajoules per kilogram. The highest from nuclear fission is about 82 trillion joules per kilogram. Nuclear fusion, if achieved efficiently, is roughly 350 trillion joules per kilogram. These are enormous numbers by any everyday standard. But they are not enough. Not for the speeds and distances of interstellar travel, not for a spacecraft of any practical size. The theoretical maximum is complete conversion of mass to energy, the full E equals mc squared, which yields roughly 90 quadrillion joules per kilogram. This is matter-antimatter annihilation, the process by which a particle and its antiparticle combine and convert their entire mass to photons. The energy density of complete matter-antimatter annihilation is roughly 10 billion times greater than nuclear fusion. It is the limit set by the laws of physics themselves. No process can release more energy per kilogram of fuel, but antimatter is extraordinarily difficult to produce. Particle accelerators generated in tiny quantities at enormous energy cost, and storing it requires magnetic traps that consume power continuously. The quantities needed for any real interstellar mission are completely beyond any technology we possess or can plausibly develop in the near term. Enter the Kugelblitz drive. The Kugelblitz drive is not a metaphor or a vague aspiration. It is a specific theoretical propulsion concept with calculable parameters, analyzed seriously by physicists using standard general relativity and quantum mechanics. Its most detailed published treatment appeared in a 2009 paper by Lewis Crane and Sean Westmoreland, two physicists who worked through the numbers with the kind of rigorous, unromantic attention to detail that separates serious theoretical engineering from wishful thinking. The basic concept is elegant. You create a Kugelblitz, a small black hole made from focused high-energy radiation, with a mass chosen to give it a useful Hawking temperature and a useful evaporation lifetime. You position this Kugelblitz near a parabolic reflector at the rear of your spacecraft. The Kugelblitz radiates Hawking radiation in all directions, because Hawking radiation is isotropic, equally intense in every direction. The parabolic reflector behind the Kugelblitz intercepts the Hawking radiation that would otherwise be emitted backward toward the direction of travel and redirects it, collimates it, focuses it into a beam directed rearward away from the spacecraft. This directed beam of radiation carries momentum. By Newton's third law, the spacecraft is pushed in the opposite direction, forward. The Kugelblitz drive is, at its core, a photon rocket. A rocket that uses photons as its propellant, expelling them backward to generate forward thrust. Photon rockets are the theoretically optimal rocket design because photons travel at the speed of light and therefore carry the maximum possible momentum per unit of energy. But conventional photon rockets require an energy source to generate the photons, and no energy source we know of is compact and efficient enough to generate photons with sufficient power to propel an interstellar spacecraft. The Kugelblitz solves this problem by being its own photon source. The Hawking radiation is generated by the physics of the event horizon, not by any external power supply. You do not need to carry fuel to generate the radiation. The black hole generates the radiation by itself, by virtue of being a black hole, by virtue of the quantum mechanics of the vacuum near the event horizon. The propellant, in a very real sense, creates itself from the mass energy of the black hole. The efficiency of this process, in terms of energy released as radiation per unit mass of the Kugelblitz, approaches 100% as the evaporation proceeds. The Kugelblitz converts its mass to Hawking radiation with nearly perfect efficiency, limited only by the small fraction of the radiation that is not intercepted by the reflector and the small fraction that is emitted as massive particles rather than photons. In principle, a Kugelblitz drive is the most efficient rocket propulsion system that the laws of physics permit. Crane and Westmoreland worked through the specific numbers for a plausible interstellar mission. They considered a Kugelblitz with an initial mass of roughly 400,000 metric tons, equivalent to about 4 fully loaded aircraft carriers or a modest office building's worth of material. This Kugelblitz would have a Schwarzschild radius of approximately 600 femtometers, which is smaller than a typical atomic nucleus by a factor of several. It would be, in every ordinary spatial sense, invisible, a point smaller than an atom with the mass of hundreds of thousands of metric tons, expressing itself only through its gravity and its Hawking radiation. The Hawking temperature of this Kugelblitz would be approximately 27 trillion Kelvin. This is a temperature so extreme that saying it in words does not convey its nature. The surface of the Sun is about 6,000 Kelvin. The core of the Sun is about 15 million Kelvin. A supernova produces temperatures of hundreds of billions of Kelvin. The Hawking temperature of a Kugelblitz drive system would exceed even these extremes, approaching the temperatures of the very early universe in the tiny volume near the event horizon. At this temperature, the Hawking radiation power output would be roughly 160 petawatts. A petawatt is 1 quadrillion watts. 160 petawatts is several times the total power consumption of all of human civilization today, released continuously from a point smaller than an atom. This is the power plant of the Kugelblitz drive. The spacecraft propelled by this drive would accelerate continuously. The acceleration would depend on the mass of the spacecraft and the fraction of the Hawking radiation intercepted by the reflector, but reasonable assumptions give accelerations on the order of a fraction of Earth's gravity, sustained over years to decades. This modest but sustained acceleration would eventually bring the spacecraft to velocities approaching a significant fraction of the speed of light, enabling it to cross the distances to nearby stellar systems in timescales of decades rather than millennia. The evaporation lifetime of this particular Kugelblitz, as it gives up its mass to Hawking radiation, would be approximately 90 years. A convenient lifetime, long enough for a mission to Alpha Centauri and back with time to spare. Long enough for a one-way journey with the original crew still alive at arrival. The Kugelblitz does not last forever. It evaporates, and in its evaporation, it propels the spacecraft. Imagine the ship, not a sleek and cinematic vessel of science fiction, polished and aerodynamic, but a real engineering structure, massive and functional. At its core, surrounded by radiation shielding of extraordinary thickness, the parabolic reflector. Behind the reflector, invisible to any sensor that relies on visible light, a point of space where the geometry has been sealed by the physics of light and gravity. The Kugelblitz, hot beyond any ordinary description, radiating with the power of several civilizations. Slowly, continuously, converting its mass to radiation that the reflector directs rearward. The ship accelerating forward, quietly, continuously, year after year, into the dark between the stars. The crew, if there is a crew, would be deep inside the ship, shielded from the Hawking radiation by layers of material and geometry. They would feel the acceleration as a gentle, constant push, not the violent thrust of a chemical rocket launch, but the patient, steady, irresistible accumulation of velocity. They would watch the nearest star slowly grow brighter over the years, shifting in color as the ship's velocity became a significant fraction of light speed, and relativistic effects began to alter their perception of time and space. And behind the ship, at the focal point of the parabolic reflector, the Kugelblitz would continue its patient dissolution, converting mass to radiation, shrinking year by year, its temperature climbing slowly as its mass decreased, its luminosity rising gradually as the evaporation accelerated. At the end of the mission, or at the end of the fuel supply that is the Kugelblitz itself, the remaining mass would evaporate in a final burst of radiation, a brief and violent explosion of whatever remained, and the drive would be silent. This is the Kugelblitz drive, the most powerful engine that the laws of physics permit, built from the most extreme object that general relativity allows, exploiting the most unexpected prediction of quantum mechanics applied to gravity. It requires no new physics. It requires no exotic matter, no negative energy, no violations of causality. It requires only the physics we already know, applied at scales of energy and precision that dwarf anything we have achieved. The practical obstacles are immense. Creating the Kugelblitz in the first place requires focusing an amount of energy equivalent to hundreds of thousands of metric tons of mass energy into a volume smaller than an atomic nucleus, simultaneously from all directions, with a precision that no current or foreseeable technology approaches. Crane and Westmoreland estimated that the power required to create the drive Kugelblitz would require harnessing a significant fraction of the total output of the Sun, suggesting that Kugelblitz drive technology belongs to what is called a Type II civilization on the Kardashev scale, one that can utilize the complete energy output of its host star. We are far from this. We are, in the Kardashev framework, barely a Type I civilization, one that can harness the energy resources of a planet. The gap between where we are and where we would need to be is not a gap of decades or centuries, but potentially of millennia. The Kugelblitz drive is not a near-future technology in any realistic sense, but the laws of physics do not forbid it. And that is the extraordinary thing, the thing that separates the Kugelblitz drive from other fantastic propulsion concepts that populate science fiction. It is not forbidden. It requires no new physics. It is possible, in the precise sense that the laws of the universe as we understand them permit it. It is distant. It is difficult. It is almost unimaginably challenging. But it is possible. Somewhere in the observable universe, if the estimates of the abundance of technological civilizations have any foundation, there may be minds that have crossed this threshold. There may be ships, right now, in the interstellar dark, propelled by tiny artificial black holes made of light, covering the distances between stars at significant fractions of the speed of light. The Kugelblitz drive may already exist, built by hands we have never seen, exploiting physics we only recently understood. And in the night sky you are under right now, among the stars you could not count even on the clearest night, there may be destinations that such ships have already reached. Places where the Kugelblitz drive has made the answer to the question of whether we are alone something other than silence. Let us gather them, slowly, one by one, and let them speak to us as a whole. We began with a question: can light be heavy? The question seemed almost playful when we first posed it, the kind of paradox that a clever child might ask, and an adult might smile at and set aside. But we did not set it aside. We followed it, and in following it, we found that the universe had a serious and precise and slightly unsettling answer. Yes, under the right conditions, at the right density, concentrated into the right volume and compressed beyond the right threshold, light is not just heavy. It is the heaviest thing that physics permits. It is gravity itself, born from the most massless substance in the universe, folding space around itself until the space has no outward direction remaining. We learn what mass really is. not the solid and irreducible thing we once imagined, but a form of energy, a concentrated and organized form, interchangeable with other forms at the rate set by c². We learned that photons, for all their weightlessness, carry energy and momentum, and that energy and momentum curve spacetime, which is what gravity is. We learned that the equations of general relativity make no distinction between mass and energy when it comes to curving space. They respond to all of it, and at sufficient densities, they respond the same way regardless of the form the energy takes. We learned about Carl Schwarzschild, who found the critical radius that defines a black hole, doing his most important work in the middle of a war from the mind of a man whose time was running out even as his equations were becoming immortal. We learned about John Wheeler, who gave so many of physics' most vivid ideas their names, who saw the Kugelblitz as a demonstration of the deep unity between matter and energy, and who spent his career arguing that the universe is stranger and more unified than our everyday experience suggests. We walked through the geometry of the event horizon, not as an abstract concept, but as a real transformation in the shape of space, a place where the outward direction ceases to exist, where every path leads inward, where the universe's geometry itself becomes the seal. We sat with the luminous horror of the moments before the event horizon forms, the blindingly intense ball of gamma radiation that is a Kugelblitz approaching its threshold, and we felt the total contrast between that maximum of brightness and the maximum of darkness that follows it, instantaneously, without warning, in the moment the geometry crosses its boundary. We traveled back to the early universe, to the radiation-dominated era when the gravity of light shaped the entire cosmos, when the conditions everywhere resembled the conditions inside a Kugelblitz, when the universe itself was made of the same fire that a Kugelblitz contains in a microscopic volume. We recognized the Kugelblitz as a piece of that ancient state, a relic of the beginning, a fragment of the conditions from which everything we see today ultimately descended. We understood that creating a Kugelblitz would be, in a very precise physical sense, recreating a bubble of the early universe in the cool and structured middle age of the cosmos. We met Hawking radiation, the unexpected discovery that black holes are not permanent, that they glow, that they evaporate, that the geometry that admits nothing can still, through the quantum mechanics of the vacuum, leak energy slowly back to the universe. We understood that for a small Kugelblitz, this leaking is not slow at all, that a microscopic black hole made of light would be hot and bright and short-lived, evaporating in seconds or minutes or years depending on its mass, ending in a burst of energy that releases all of its remaining mass according to E equals mc². We dreamed with Crane and Westmoreland of the Kugelblitz drive, the engine that exploits Hawking radiation to propel a spacecraft between the stars. We imagined the ship, the parabolic reflector, the invisible point of extreme physics behind it, radiating with the power of several civilizations, slowly converting its mass to thrust, patiently accelerating toward a distant star over decades of quiet travel. We acknowledged both the extraordinary promise and the extraordinary danger of this concept, the knife's edge between the most powerful engine and the most powerful explosive that physics permits. And we sat with the cost of creation, the energy cost and the engineering cost and the deeper cost, the philosophical and ethical weight of creating a piece of the early universe, of wielding the fire that belongs to the beginning of everything, of crossing a threshold that demands from any civilization that crosses it everything it has in terms of wisdom and capability and restraint. Now, at the end, let us ask the question that the Kugelblitz ultimately poses. Not a question about physics, a question about meaning. What does it mean that the universe contains this possibility? The Kugelblitz is not a thing that exists today in any natural form we know of, and in no artificial form that we have created. It is a theoretical object, a prediction, a logical consequence of equations that were written down more than a century ago, and that have been tested and confirmed to extraordinary precision in the centuries since. Every component of the Kugelblitz prediction rests on physics that is well established. The equivalence of mass and energy, the curvature of space-time by energy and momentum, the Schwarzschild threshold, the geometry of event horizons, the quantum mechanics of the vacuum and Hawking radiation. None of these are speculative. None of them are frontier hypotheses awaiting confirmation. They are the foundations of modern physics. The Kugelblitz follows from those foundations as inevitably as any mathematical theorem follows from its axioms. The universe's laws permit it. More than permit it, they predict it. They say, if you do this and this and this, if you concentrate this much energy into this small a volume, a black hole made of light will form. The universe is not ambiguous on this point, and that tells us something about the universe that goes beyond the specific case of the Kugelblitz. It tells us that the universe's laws are consistent at every scale, including the scales we have never visited and may never visit. It tells us that the equations we have derived in laboratories and observatories apply equally in the most extreme circumstances we can theoretically describe. It tells us that physics is real and complete, and that following it honestly to its most extreme conclusions leads to real predictions about real objects that might really exist. There is something deeply reassuring about this, even though the object itself is extreme and dangerous and strange. A universe whose laws are consistent, that does not break down at the extremes, but simply continues to follow its own logic into ever more violent and alien territory, is a universe that is, in a deep sense, trustworthy. Not comfortable, not designed with our comfort in mind, but trustworthy. The rules are the rules, everywhere and always, from the gentle photons warming your closed eyelids to the gamma radiation seething inside a Kugelblitz event horizon. The same physics, the same equations, the same universe. And there is something inspiring about it too. The fact that the universe contains the Kugelblitz as a possibility means that it contains, within its laws, more richness and more strangeness and more extreme territory than any generation of humans has ever fully explored. We have been doing physics seriously for a few centuries. General relativity has existed for just over 100 years. Quantum mechanics is younger still, and already, following these young theories to their logical conclusions, we find predictions of objects so extreme that they have no natural counterpart in the universe as it currently exists. Predictions of engines that could carry life between the stars. Predictions of conditions that recreate the beginning of everything. What do the next centuries hold? What do the equations still unwritten contain? If a century of physics leads to the Kugelblitz, what does a millennium lead to? The universe is not going to run out of strangeness. It is, if anything, more strange the further into it you look. There is a philosophical tradition, ancient and widespread, of the idea that the deepest truths of reality are also the most dangerous. That knowledge carries responsibility. That understanding is not neutral, but demands something of the one who achieves it. The fire myths of human cultures, from Prometheus stealing fire from the gods to the Hindu Agni to the countless other stories in which fire represents knowledge and power and the potential for both creation and destruction. These stories are not about fire literally. They are about the nature of understanding, about what it costs to know the most powerful things, about what it asks of the one who knows them. The Kugelblitz is the modern version of that ancient theme. The fire of the gods, realized in the equations of general relativity and quantum mechanics rather than in mythology. The knowledge that carries the highest possible stakes. The understanding that demands the most from whoever possesses it. We do not possess it, not yet, not in the sense of being able to act on it. We possess the equations. We possess the understanding of what the Kugelblitz is and what it would take to create it and what would happen if we did. That is not a small thing. It is the first step. Knowing where you are going is not the same as being able to go there, but it is not nothing either. Knowing where you are going changes how you see the path. It changes how you think about the universe you inhabit. It changes what kind of entity you understand yourself to be, dwelling in a cosmos that contains, as one of its logical possibilities, the fire of the beginning temporarily recreated in a microscopic volume, sealed in its own darkness, radiating with the energy of thousands of stars, waiting to carry some future civilization to the stars. Light can become a black hole. The most familiar thing in the universe contains within it, at the extreme end of what the laws of physics allow, the most sealed and most extreme thing in the universe. The warmth of sunlight and the darkness of a Kugelblitz are not opposites. They are the same physics applied at different scales, the same equations, the same universe, one gentle and one extreme, both real. And here, in this quiet room, with whatever soft light remains in the space around you, with your breath slowing and your body settling into the surface beneath you, you carry the knowledge of both, the gentle and the extreme, the familiar and the alien, the ordinary light of an ordinary evening, and the extraordinary darkness that the same physics allows when the light is concentrated beyond all ordinary limits. This is what it means to understand physics deeply, not just to know the equations, but to follow them where they lead. Not just to describe the comfortable middle of what exists, but to trace the edges of what is possible. The Kugelblitz lives at those edges. And in reaching those edges, in following the logic of light and gravity to their most extreme conclusion, we have also reached something else. A more honest picture of the universe we inhabit. Not a comfortable picture, not a safe picture, but a true one. A universe that contains gentleness and extremity, warmth and violence, the soft glow of a candle and the blinding fire of a ball of light sealing itself into a black hole. A universe that is consistent and uncompromising and indifferent to our preferences, but that is also, for those willing to look at it honestly, incomparably strange and incomparably beautiful. The Kugelblitz is a part of that beauty, the most extreme part, the part that sits at the very limit of what the equations allow and says, the universe goes this far. The universe permits this. The universe, followed honestly to its deepest conclusions, leads here, to a black hole made of light, to the heaviest thing that can be made from the lightest substance, to the darkest thing that can arise from the brightest process, to the fire that belongs to the beginning of everything, waiting in the mathematics for the civilization wise enough and capable enough to find it. And now, with that image settled somewhere in the quiet space behind your thoughts, let the night have you. Let the equations rest. Let the event horizons seal themselves away into the theoretical space where they live. Let the Kugelblitz be what it is, a prediction in the physics, a possibility in the universe, a fire in the equations that does not burn anything tonight. The room is quiet. Your breath is slow. The light around you is gentle and ordinary and safe, carrying none of the extreme weight it could carry in principle, and all of the warmth it carries in practice. The universe is vast and strange and consistent and extreme and also, right now, in this moment, perfectly quiet. The Kugelblitz waits in the equations, patient and sealed and ancient and possible. And you are here, knowing it exists, carrying that knowledge gently into the dark. Sleep well. The fire of the gods is far away tonight, and the light in your room, soft and ordinary, knows the way to places you have only just begun to imagine. It does not need to become a black hole to be extraordinary. It only needs to reach you, here, now, in this quiet moment, doing what light has always done since the first moment of the universe, crossing the dark to find you.